I'm Peng from Crop Sciences here at U of I. I'm the assistant professor for water quality and the faculty extension specialist working on nutrient loss reduction strategy. I'm involved in the science team for the nutrient loss reduction strategy. I'm chairing this committee this year. So today I'm gonna talk about the nutrient 2.0, right? So I'm gonna explain why we want to do a 2.0. What is that? And what does it mean for Illinois? And we're gonna cover a lot of these things at the state level, so shifting from Shalamar's presentation from the field scale to the whole state level. And I want special thank my lab members, especially Chen Yu and also Yuanxin, who gonna present their posters during noontime and also in the afternoon. So please check out their posters for a lot of the detailed results and also the methodologies there. So as David just introduced, so I'm from Crop Sciences. I'm leading the Water Agriculture and Conservation Innovation Lab, which is WASI. So every time I give presentations, I try to promote my lab and also my research and extension program. So this is the landscape that we have been working on, right? So we have cropland, and we have streams, we have edge of the fields, and how the nutrient is transported from the fields to the river and to the waterways. I think that's a key topic for the NREC community here. So why do we need Illinois nutrient loss reduction 2.0, and what is that? Are we not doing a good job in the past? No, not at all. So we are doing a fantastic job in the first 10 years of Illinois nutrient loss reduction strategy. We have been keeping updating the progress. We have published progress report every 2 years, and we are developing a lot of the dashboard and data layers to support the reporting there. But why we care about 2.0 is that there is still a long way to go. For example, here in this graph from the biannual report from last time, so we got the short-term goal and we got the long-term goal there. The timeline is 2025 for short-term and 2035 for long-term. But we are still showing, for example, nitrate increasing, phosphorus also increasing. I mean, from the absolute nutrient loading perspective, right? So there is still a long way to go for the nutrient loss reduction strategy. And so that's the general background for the 2.0. And we have been working on this for 10 years, right? We published the first nutrient loss reduction strategy in 2015. That's last year is exactly like the 10th year. And we have seen many, many shifts, right, in terms of focus. Maybe we care more about the downstream hypoxic task force or Gulf of Mexico in the past, but now we focus more on local drinking water, right? Whether our watershed is clean enough, whether our ecosystem is really sustainable. And we have a lot of the R&D advancement in the past. Over the past 10 years, NREC has funded a lot of these projects, studying cover crops, studying different rotation system and different nutrient management system. We have accumulated a lot of data, and we have done a lot of the watershed scale demonstrations, and we enhanced the modeling and data-driven modeling capacities in the past. So how we can really integrate those advancements in the next phase and next 10 years of the nutrient loss reduction strategy, I think that's the key here, and that's why we want to talk about 2.0. And this is a timeline I leveraged from the Minnesota. So they published their next 10-year nutrient loss reduction strategy early this year or last December. So you see this is a timeline. So they almost have a similar timeline with us, right? They published their first nutrient loss reduction strategy in October of 2014. And then 2024 is their 10th year. And then they initialized a working group and trying to revise and updating the nutrient loss reduction strategy. Here I'm not talking about biannual progress report. I'm really talking about how you are really shifting some of the framework and also integrate the most advancement into that strategy for the state. So I was in DC last time at federal EPA, joining the hypoxic task force public meeting, and also joining the Sierra 46 annual meeting there in DC last week. And I was hearing different states reporting their progress to the federal EPA. And I'm trying to capture some of the keywords there, how they are using data, how you are using new evidence, and how they are updating or revising their nutrient loss reduction strategy. So this is a table that I summarized. Maybe some of those numbers are not accurate enough, but give you some sense about which states are working on the nutrient loss reduction strategy, when did they release their first version, and whether they are updating or not, and which year they plan to update or revise their nutrient loss reduction strategy, right? So again, I want to emphasize here, I'm not talking about the biannual, annual progress report here. I'm really talking about whether the framework is shifting, whether the new evidence, new methodologies, new data-based evidence is incorporated in the framework. For example, whether are we updating some of those priority watersheds? Are we really make different appropriate appropriations or allocations of those loading in the rivers? And are we consider different sources? Those kind of factors are really the key factors I'm talking about for the nutrient loss reduction strategy 2.0. So I just mentioned Minnesota, they published their 2025 version of nutrient loss reduction strategy. It's a quite detailed document, so I'm gonna get into a little bit details there. And Wisconsin, so their Department of Natural Resources are also working on this. And if you see Iowa, so this is a news release from Iowa, so they want to modernize their nutrient loss reduction strategy. It has been 10 years, so they use the modernized term there. But I like it because it details some of the thought process, right? So we have a lot of the progress in the past and how we can really revise this strategy to incorporate those new evidences. And also this is a paragraph I borrowed from the Louisiana nutrient loss reduction strategy. So they are also keep revising their nutrient loss reduction. So it's a living document, right? So it should be updated once we have some of the progress, we have some of the new evidence, and then we can keep working on the nutrient loss reduction for the state. So as I just mentioned, so this is an example from Minnesota. I use the Minnesota example here. It's not just because they have released their nutrient loss reduction strategy. I just want to get into a little bit details what they have been working on, right? So what has been included in the nutrient loss reduction strategy? And if you see some of those chapters in this document, you're gonna see, for example, they shifted from the whole basin scale, Mississippi River Basin in the first 2 chapters, and then quickly to the local state level, and then different watersheds and different sources, for example, urban watersheds, agricultural watersheds, and how they're gonna work on. And then they also trying to give a clear timeline, updated timeline, whether this existing timeline is still working, how are we gonna deal with that, right? So I think a lot of the stakeholders are really trying to see, is that original framework still applying to the new issues that we are facing under, for example, enhanced precipitation, right, in the spring, and a lot of the land use change, and the shifting nutrient management practices, adopting more cover crops. So how those new changes gonna be incorporated in the nutrient loss reduction strategy 2.0. I want to convince you that we may need some of the paradigm shift. So I want to propose, maybe we need an integrated field to watershed approach for the non-point sources. So why, and what is that field to watershed approach? So it's just because in the past, there has been some of the disconnection between the field scale adoption and also watershed scale progress tracking. And we know that within field practices like nutrient management, cover crops, no-till, those BMPs has a great potential in meeting the nutrient loss reduction strategy goals. And they represent the majority of the land, and they have the majority of the potential there. But we also understand non-point source nutrient losses cannot be resolved by only relying on the within field practices. So for example, in the high flow condition, once we get the extreme precipitation, when the flow is really, really high, we still got a lot of those nutrient loading in the streams. It's just because there is nutrients there and there is high water flow and the nutrients gonna be flushed out. And how we gonna deal with those situations? Are there existing BMPs that can work with those conditions? We have no clear answers for those type of questions. And also the legacy nutrient issues usually goes beyond the field. We definitely have the legacy nutrients in the soil, but we have a lot of those nutrients in the streams, in the floodplains, in those downstream areas of the watershed. So that's why I'm really trying to push the philosophy for the nutrient loss reduction strategy, we really need an integrated field to watershed approach for controlling the non-point source pollution here. And what is that? So here is a brief example. From the field to watershed scale, we can quantify when you adopt cover crops or improved BMPs, what are going to be the nutrient or water quality impacts at the watershed scale. And vice versa, if we have a target for a specific watershed, we can inform the field scale adoption or the conservation planning at the field scale. So how much cover crops do we need for our watershed if we really want to achieve that goal? And where we should put it, right? Some of those edge of the practices, where we should put it. So those kind of answer those questions are gonna really matter for how effective we are in reducing the nutrient loading for a specific watershed. So as I just mentioned, there are several key questions to be answered in the research. The first one is where we should target, where we should prioritize, which part of the watershed we should prioritize at the watershed scale. The second question is really about how we're going to achieve, right? What are the sources? What's the contributions, right, from different sources? And how much of the contribution is coming from stream event, and how much contribution is coming from the base flow period? And finally, what is the conservation plan, right? Do we have a concrete conservation plan, science-based conservation plan for a specific watershed that can really guide the implementation, and also on-the-ground practitioners like farmers or watershed specialists, how they can really do the conservation for our watershed, and what is the conservation plan? So I think those three questions are the key guiding questions for my research in my research group at the watershed scale. And also, we are trying to link the field scale practices to the watershed scale outcome. And this is not done yet, right? So after we answer those three questions, so we should engage with different stakeholders, like all of you here, trying to form this partnership and get the conservation plan implemented for a specific watershed. So we got the implementation and the partnership stage. And finally, we need to continue monitor and also tracking the progress for that watershed or for the state. So this is a loop. This is not a one-stop solution, right? So it's an iterative process. And I just mentioned, we got first version or first phase or first 10 years of the nutrient loss reduction strategy. And now we are entering into the second 10 years. And so we should keep iterating the original nutrient loss reduction strategy, some of the source attributions, and also different frameworks there in the nutrient loss reduction strategy. Okay. So what do we mean by answering those three questions? So where? So I think the first thing is that we're going to develop some of the nutrient inventory, quantifying the nutrient export trend, quantifying the seasonal variations. For example, how much is coming from extreme rainfall precipitation events, and how much is coming from the base load period or the summertime, and what are the driving factors for those changes at the watershed scale. And second one is really bridge some of the knowledge gaps from the field to watershed scale. And we understand agricultural source is not the only non-point source for the agricultural watershed. We have stream bank erosion, right? We have other non-point sources from other land use cases. And how we really quantify those sources and their contribution to the watershed scale nutrient loading. And how do we quantify those legacies, either in the farmer's field or beyond the farmer's field? And how much BMP is really needed for a specific watershed. And finally, we need to really have a concrete conservation plan from the field to watershed scale. I think those are some of the gaps that we have been thinking. And this is a graph I used in one of my proposals last year, and trying to develop this type of integrated field to watershed scale approach. And we really need interdisciplinary expertise, like crop sciences, hydrology, soil biology, chemistry, and also some of the geospatial big data and also modeling techniques. And we really need to base our nutrient loss reduction strategy 2.0 based on the data, right? Based on the evidence. It's not we need to make it objective. It's really evidence-driven. And science-based integration and stacking of different BMPs at the watershed scale. And finally, like we have this consolidated partnership and the stakeholder engagement for the watershed at both state level and also local level for the nutrient loss reduction strategy. So some of you may have seen this table, right? So we have been talking about what are the gaps for the current research. So this is a table that we summarized for some of the gaps for the research, where to target and how to reduce, and what is the conservation plan. And as you can see, like NREC funded my projects last year to develop the statewide and annual nutrient surplus and export nutrient inventory. I'm gonna talk about that in 1 minute. And also, like there are some other like gaps that haven't been funded. For example, temporal variation, right? Source attributions, like quantifies the legacy, partially funded to Andrew for stream bank erosion, and I have also been working on that. So, and also like efficacy, right? So what is the uncertainty, and how effective are those BMPs, either at the field scale and also watershed scale? How much BMPs do we need? And what is the conservation plan? So those are some of the gaps at the high level, definitely. This is not going into very detailed, but some of those gaps are really, we need to find some of the concrete answers to those questions such that we can really make some of the progress and also substantiate our progress into the future 10 years. So I'm gonna report some of the initial results and preliminary results about the NMP budget at the watershed scale. So when we talk about NMP budget as a watershed scale, so here is a simple, very simple mass balance equation. So we got the storage change on the left-hand side, and we also got the input and output flux on the right-hand side. So you can see like we got like nutrient storage in the soil, in the groundwater, and also in the river sediment. And we also got the nutrient surplus, right? So when we talk about surplus, it really means like how much we get into the system and how much we removed by harvesting the crops. So that's that term, that residual term there, or like I should not use residual because there is another residual term in this equation. But that surplus means like how many excessive nutrients are we getting into the system. And then for our watershed, we definitely have a major output component there, which is the river export. So that is the river export component there for the nitrogen. And also similar equation can be written by for phosphorus. And we got the storage pools on the left-hand side. We also got this like surplus and export to the right-hand side. And how we can develop this budget and trying to integrate both surplus and also export to quantify the progress and also understand what is limiting and also what is driving the nutrient loading in the rivers. I think that's the key for this project. So this is a GIF animation that we finished like yesterday. So it's fresh. It's fresh. So we basically combine the existing data layers, for example, from the National Nutrient Inventory, from our data-driven spiral modeling, which is also used by USGS, and we try to combine different data sources and to see what are the overall budget for the whole state, from 1980s to 2017. Okay, you may ask why you stop at 2017, because there is some of the data limitations there. So from USDA, and we are also working with IFCA trying to rely on their fertilizer survey data across the states and trying to update the surplus component. So you may see that this is like, there is variabilities there, right? There is spatial pattern, like which part is having more surplus and which part is having more river export. And you can also see like there is year-to-year temporal variabilities here, right? So for example, that blue line represents the surplus, which is like how much excessive nutrients are getting into the watershed. And that red line is the river export. So definitely it can vary with the hydrological variability. For example, wet years versus drought years. So that term gonna be a little bit different. And then by taking those difference, you're gonna get the residual term, which largely represent how much nutrients are stored in the system. And we can do similar things for phosphorus. And as you can see, like the phosphorus input or the surplus term has been declining over the past 30 years. We have been seeing that declining trend, right? And the export is kind of like stable, at least stable, from year to year. And then we can also see like we are diminishing some of the storage term. But why we are not making meeting that nutrient loss reduction goal for phosphorus. I think there is a lot of the hypotheses about legacies, about different retention capacity for the watershed there. So we really don't have a clear answer at the current stage. So that's why we need the research here. So what we can do with this type of like statewide and high resolution nutrient budget, what we can do. So I'm gonna show some of the examples here. So what we can do after we get those like high resolution statewide nutrient budget, we can really use this type of information to prioritize different watersheds. So here I'm showing a framework that we developed. On the x-axis is the nitrogen surplus, and on the y-axis is the nitrogen export. And nitrogen surplus represents how much excessive nutrient is getting into the river, is getting in the watershed, and nitrogen export is really about the river system, right? So basically we are really integrating both input and output term here and trying to see what's going on with our particular watershed. Is there any trend? Is that decreasing or increasing trend there? How much is the nutrient use efficiency there? And how we can really use those information to prioritize different watersheds. So that's the first step, basically prioritize watersheds. And second one is really, once we have those detailed statewide nutrient inventory, we can really analyze different driving factors, right? And assigning some of the most appropriate practices or BMPs to a certain watershed. And we can also design the scenarios for this state. And we can update the scenario design. And a lot of you may see the scenario design for the nutrient loss reduction strategy. And we can add more details and also revise those scenario design and quantify the economic investment or economics for those scenarios. So that's kind of the end goal here, why we are developing those and how we can use those information to support the nutrient loss reduction strategy 2.0. And a brief example here is that we did this type of analysis for the upper Mississippi Basin. And you can see like we really need some of the prioritization here. Like a brief sentence here in the end, the highly targeted class comprise a quarter of those watersheds over the whole basin, upper Mississippi Basin. But those 1/4 of the watersheds are contributing around like 65% of the nutrient loading. So basically we have some of those hotspots over those watersheds. It's not like we have homogeneous nutrient loading or nutrient losses from the watersheds. We really need to see the big picture as a whole state and then see which watersheds can be prioritized and what type of factors are driving those nutrient loading in the rivers. And we can, as I just mentioned, so we can analyze the underlying drivers from the source components, like how much fertilizer we are putting in, how much manure we are applying, and how much crop yield we are harvesting. And then we can also analyze different delivery factors, like whether this soil is sandy, and with how much cover crop are we having, how much CRP land are we having in those watersheds, and transport processes like the river system. And we can use those factors and trying to assign the BMP, corresponding BMPs to resolve some of those issues, right? So this is like evidence-based. So there is a logic there. So we first see those high loading hotspots, and then we get into the details and trying to analyze underlying drivers, and then we assign the BMPs like for those watersheds and trying to update those scenario designs. And we can also quantify the economic impact. So as you can see, like as you can imagine here on the x-axis here is whether we consider crop yield drags or crop yield loss penalty for some of those BMPs, like cover crops or reducing the fertilizer rate, and whether we consider those. Like no, like basically we didn't consider the crop yield loss. And no, medium, and high, we basically give some of the yield penalty there. And then the total cost for the goal for the whole upper Mississippi Basin, if we want to reduce the nitrate loading by 15%, what is the total cost there? And as you can see, like highly targeted always gives you this type of most cost-effective approach here, compared with like low target. Basically, you apply the same strategy, and you apply the same like BMP, same type of BMPs across the whole Mississippi Basin, without any like information-based or evidence-based prioritization there. So that's the key here. And we can also use those new NNP budget and trying to develop, understand what is a temporal change, right? What is a temporal change? For example, we quantified the nitrate export over the upper Mississippi River Basin and see what's going on and which part is increasing and which part is decreasing. And we further differentiate that into both human contributions and also hydrological contributions. This is something very important because we are doing a lot of the BMPs on the ground, but the hydrological system is also changing. So we got more precipitation, and also the precipitation seasonality is also changing. And how we can consider those factors in quantifying or in tracking the nutrient loss reduction progress, I think that's the key here. And our contribution here is really separated out and see like which part is contributing more over this whole basin scale. And we can see like Minnesota and Iowa, they got both contributions from human activities and also hydrological variabilities. But for Illinois, northern part, we got a lot of those hydrological changes over the past 10 years or 20 years. So at least from this study. And you can also see like different watersheds, right? HAC 8, different HAC 8 watersheds, and how those HAC 8 watersheds are really performing and are really making some of the progress in those different sources and also different contributions from the human impact and hydrological contributions. So I highlighted like Illinois River Basin here, 0712 and 0713. So you can like, if you compare with the average upper Mississippi River Basin, which are the first group of bars, so you can see like we are almost like on the average there, and sometimes we are even doing better than the average. And we can also quantify what is driving this nitrogen loss to water ratio. And you can see like nitrogen loss to water ratio is defined as how much is exported and how much compared with how much is the excessive nutrients in the watershed. And how much of the nitrogen surplus is getting into the waterways. So that ratio is quantifying how much nitrogen is getting into the waterways. And we can see a lot of those watersheds are increasing over the past 20 years. But underlying drivers, so we see like forest, wetland, tile drainage, precipitation, air temperatures are some of those underlying driver factors for those like nitrogen loss to water ratio changes over the past 20 years. And we can use this information to categorize different watersheds into different tiers or into different groups. So, and I think as a state level, this type of information is gonna be very useful to group different watersheds into different tiers. And then we have different strategies for different tiers there. And we can also quantify like how much of those changes in the nitrogen loss to water ratio is contributed from the anthropogenic activities, for example, CRP, and how much of those are contributed by the hydrological change. And we see this nitrogen loss to water ratio is largely controlled by this precipitation variability changes in the hydrological system. So that is for the first part, for the nutrient and phosphorus loading or inventory. So how we are tracking the nutrient loss reduction progress now? So as you can see here, we got the increase 4.8% increase for nitrate loading, and also 35% of increase for phosphorus loading. But we also see like 23% of this like discharge increase for the whole state. But this is not like this is not for the flow normalization. We didn't consider the hydrological variability here. So what we did is that we take the same data. I just skip some of the methodology here, and I want to highlight some of the results. So we take the same data, and we follow the same methodology for the nutrient loss reduction strategy, and how we quantify from different single watershed and single stations, and aggregate that to the state level. And here is some of the results. And as you can see, when you consider flow normalization and when you don't consider flow normalization, sometimes we are getting opposite progress reports, right? So for example, here in the biennial report, and we got the increased trend, and if we do the flow normalization, stationary flow normalization, so we're gonna see some of the decrease. And that is for nitrogen, and this is for phosphorus. So we got 35% for the last biennial report. But if we consider the contribution from hydrological variability, we're gonna see like 72% increase from the whole state. And also, like there are gonna be some of the variabilities there, depending on what type of methods we are using. But the key highlight here is that are we going to adopt the 5-year average type of like absolute value, or like are we going to consider the hydrological change for the state level nutrient loss reduction progress reporting? I think the key answer here is that we may need both, right? Because this is a system, this is our land, and we want to see like how much of the total loading is, and also we want to see how much of the contribution is coming from the or management or BMPs, and how much of those contributions is coming from the hydrological variability, which we cannot control to some extent. Okay, so I want to end with this summary table for the non-point source gaps. So some of those gaps we are actively addressing them, and some of those gaps we still need some of the future research to fill those gaps. And I want to take some questions if you have any.
Thank you, Ben.
Thank you.
Let's give Dr. Peng a hand.